the position of signal. And the position of signal here, like we said before, if the electron around the nucleus is available, it means it will be shielded and the chemical shift will be up. But if the electron is not available, it will be de-shielded and the chemical shift will be downfield. And this is the theory. For example, the first thing affecting the chemical shift is the electronegativity. What does it mean? When my atom, when my proton is attached to an electronegative group, it means it attracts these electrons and not, you know, it's not available. So it will be de-shielded and appears downfield. Like chloride, bromide, fluoride, oxygen, all these are electronegative groups which attract my. So for example, if I have here Hp and H proton A and proton B will be much more downfield because it's directly attached to chloride. And if we have here and here, the fluoride is more electronegative than bromide. So proton B will be also much more downfield because the electrons is de-shielded, the nucleus is de-shielded much more. Here P also is more downfield, but because we have two chlorides, but A attached to only one chloride. So the number also is a member. This is, a table for the electronegativity of other atoms. This shape, look at this simple structure. When I put chloride here, this was 0.8 and it's jumped to 3.6, and this was 1.3, it jumped to 1.7. And of course, when this electronegative is near to the atom, the effect is much higher. When it's far, the effect would be much lower. Another thing is hybridization. The hybridization, because it's affected directly on the availability of the electrons. The metals, the CH3s here, which are sp3 and hybridization, the electrons are available, so it's protected and shielded. So usually we see the metal at uh, so we usually see the metals at around the one, more than one or less than the one. But the methylenes, the S characters is more, so the electrons is not available more, the electron less available, so the atom would be a little bit higher as de-shielded, so it would be downfield. And for the S characters is the same. Another important factor is the anisotropicity. What is anisotropicity? We will talk about the anisotropicity is another effect. Let's revise with me. We will talk about that the proton itself spinning like this, and this give a magnetic momentum or magnetic energy. This energy affected by another applied magnetic field, make it two different states like we said before. And the electron around the proton is spinning, and this electrons give a third magnetic field, which is in an opposite position to the applied magnetic field. The anisotropicity is a fourth magnetic field, another one, appeared by the movement of the electrons, mostly in pi orbitals, not in sigma orbitals, but it's happens sometimes in sigma orbitals, and I will give you these examples. What does it mean? It means some electrons in pi orbitals, they spinning in another in a unique way, and this gave us a fourth magnetic field. Like what? Like the Fenner ring. The Fenner ring, appears, protons of Fenner ring, the aromatic ring, the benzene ring appears at from 6 to 8. It's highly downfield. Why? That happened because the electrons on pi electrons here in the aromatic ring are circulating in a resonance system. This fast circulation resulted in a fourth magnetic field. The direction of this magnetic field like that, here and here, which means inside the ring, the magnetic field is opposite to the applied magnetic field. And outside the ring, the direction of this anisotropic magnetic field is the same direction with the applied magnetic field. What does it mean? If I don't understand this message, pardon, there is no someone who needs to be accepted to join this program. I didn't understand you. Okay, let's go back. When if we have a proton here outside the ring, which means this proton will be affected with another magnetic field due to the anisotropicity. This magnetic field is with the same direction of the applied magnetic field, which make its much more magnetic field affected on the proton. So it will make the difference between those states, lower energy and high energy, much bigger. But if we have a proton here inside the magnetic field, it will be shielded and it will be the vice versa. Let's see here an interesting example. Look at this annular. This annular, it's a very interesting compound. Why? These are protons and these are protons, they are the same. But these protons are inside the ring. This circulating huge aromatic system make anisotropic efficacy very big. So the protons which are inside are very shielded, appears at -3, appears before the tetramethyl xenon. It's very highly shielded proton, and vice versa. The proton outside it's highly deshielded, so it appears at 9.8. They are on the same chemical position, but the anisotropicity for this pi electrons make this huge effect. Again, I will give you this one. This circulation make the magnetic field outside the ring. It's with the same direction of p node inside the ring is against p node protected. So all the protons inside the ring will be protected from the applied magnetic field and appears at -3, but the outside appears at 9.2. This also the same. If the metal is inside, it will appear at -4, but if it's outside, it's about 8. And this also the same example. The another example of anisotropicity is the double bond, the olefinic bond. The olefinic bond, we have a sigma bond, we have a pi bond. The electrons of pi bonds also has some kind of anisotropicity and they make another magnetic field. This magnetic field inside the bond is against the p node and outside the bond is with the p node. So the protons appears present on outside, so it gives a huge effect, make it much more downfield to appear at maybe 4.5 to 6 chemical shift. What happened is the vice versa, and the opposite thing happened on the acetylene bond or tribond. The tribond here, the triple bond here, we have two pi bonds and they are circulating also, but this is the photo. We will see that the induced magnetic field by anisotropicity here is with the p node and here is inside. But the protons lies on the place which is the induced magnetic field against the applied magnetic field. So we see the triple bond or the acid bond at 2.5, and it's strange. Double bond appears at 4.5 and triple bond appears at 2.5 because it's shielded because the proton here in this area, and this is the shielded area of the induced magnetic field by anisotropicity. So to review, to revise what we said, in the aromatic ring, It's highly deshielded to appears at from 6 to 8. In the double bond olefinic bond is deshielded also to appears from 4.5 to 6. But in carbonyl also, the carbonyl is very important. We will talk about it a few minutes later. And in acetylene bond, it's predicted to be appears at 2.5. Another example here, in carbonyl also the pi bond makes that because in carbonyl the pi bond makes also, where is the carbonyl? It was here. Yeah, the pi bond here in the carbonyl make another anisotropist which will make give this proton, make it downfielded. In aldehydes it appears at 11. It's highly downfielded because of anisotropicity and it's near to oxygen also. And let me ask you an important question. It's a very interesting question. It's related to the carbon 13, not the proton. Do you have an isolate this kind of compound before? If we have a compound, we call it a non-ester carbonyl. It's carbonyl, only carbonyl. There is no oxygen or nitrogen here, no oxygen or amine. This carbonyl appears in carbon at about 200, and it's okay. I will adjust something in the voice. Okay, I hope my voice is better now. If you look at this carbon, it's an ester carbon. It appears at 200, 205. But if you look at this carbon, this one is attached to one carbon, the carbonyl, and this one attached to two carbons. This is ester carbonyl, and despite that, it appears at 170 or 175. It's weird. At first case, we have a carbon attached to only one oxygen, and appears as at 205. And when it's attached to two oxygen, it appears at 170, 175. Why is that? That because this carbon is highly deshielded, not because of this oxygen, not because of the electronegativity of this oxygen. That because that oxygen is, you know, make that pi bond make an isotropicity high, put this carbon under highly induced magnetic field on the same direction with the applied magnetic field. But this one, what happened in this one? There is another oxygen here. The pi electrons here are not available because they make a resonance from here to here. The unavailability of these pi electrons make the induced anisotropicity and decrease the entropicity and make the induced anisotropic magnetic field is much weaker. So it's make the effect of this pi electron and the anisotropicity on this carbon is much less, and this give this carbon the upfield effect to be on 170. Sometimes the entropicity happen in sigma bond. For example, in this compound, the equatorial protons are lower than the axial protons with 0.5 part per million. But in the case of sigma bonds, it's a very little effect. Okay. Also, another factor is the van der Waals effect or the steric interaction. If you have cyclopropane or cyclobutane or cyclopentane, it makes difference. The steric efficacy make it highly shielded because when it's steric, the orbitals are coming together, the protons are, the electrons around the nucleus is present, much more available. Another important effect is the resonance effect. We have two kind of groups which attach to the phenyl ring. One called electron donating, which give electrons to the aromatic bond, and another one is called electron withdrawing, which withdraw these electrons. The electron donating like the oxygen, hydroxyls, amino esters, ethers, I'm sorry, and electron withdrawing like the nitro group. If we look at the resonance in electronegativity here, this is the resonance system which happen according to the delocalization of this lone pair electrons. It make high shield. The electrons are more available here in ortho and in para position. On the other side, the nitro make highly de-shield on the ortho and para position. What does it mean? It means when you find your phenyl ring attached to a hydroxyl, it means this hydroxyl will shield the ortho position. The meta will be de-shielded than the ortho because the resonance protect the ortho. So the meta, although far, it's it's the far one from the oxygen, but it's more de-shielded than the ortho because the ortho one is protected by the resonance effect. And on the other hand, if you have a nitro group on attached to a phenyl ring like this one, you have to expect that the ortho position and the para position will be highly de-shielded because the electrons are not available. This is examples for what I have said from some time. Another important example, and please focus with me. If you look at this compound, this is a carbonyl group, this is the alpha carbon to the carbonyl group, and this is a beta carbonyl of carbonyl group. From the first look, I think the alpha carbonyl will be highly de-shielded, more de-shielded than the beta, because it's much more near to the carbon. So the carbon will affect the alpha much more the beta, and this one will be de-shielded, and this one will be less de-shielded. But is this not the case? What happened is the beta carbonyl is highly de-shielded, much more than the beta carbonyl is highly de-shielded, much more than the alpha carbonyl. And why does it happen? This happens because this is a resonance effect between this two electrons and the carbonyl. These two pi electrons here move to p here, and this pi electrons move to p here as free. And in this case, the beta carbon is highly de-shielded by the resonance. So this case is called alpha beta unsaturation carbonyl, and you have to memorize it because it's happened to most of us in natural product and in synthesis. Another important case in tautomerism we have to discuss is the ketone enol tautomerism. Subcompounds, if I have compound like this one, this is a keto form. Some resonance happen, and this bond, these two electrons come here, and or these two electrons will come here, give a negative charge here, and this proton move from here to this one to make it hydroxyl group, and only here one proton. This is what we call ketone enol tautomerism. The compound has two different states. One is the ketone state, and one is the enol state, and they are different from each other. In this case, the ketone form is much more stable because there is an intermolecular hydrogen bond having here, a cyclic structure, a stable structure. This compound, when we make it soluble in a solution, it has two states. Ketone states about enol state, I'm sorry, about 85%, and ketone state was about 15%. And this compound will have each proton and each carbon will have two signals, not one signal. If you look at proton, this is the methyl in the case of enol, and this is the methyl in the case of ketone. If you look at this structure from the beginning, you will see no, it's not a one compound. It's a major compound and another minor compound, but it is not the case. If you has a ketone enol tautomerism, expect that your compound will have more than each proton, and each carbon will have more than one signal for each proton. This paper I will put it for you in the group today. This talk about the efficacy of different solvents on the tautomerism. It's published on 1966, and the effect how much just choosing the solvent, its effect on this one. Another resonance effect, it's the substituted vinyl ether. In this case, the oxygen atom shields the alpha proton with inductive and shield the beta proton with resonance. And this is and the opposite to the alpha beta unsaturated carbonyl link. So we will find the beta carbonyl here highly shielded with the resonance, and the alpha carbonyl is deshielded with the inductive effect. Another important effect is hydrogen bond, and this we work in natural product. I think anyone work in natural products have seen this before. This is called the hydrogen bonding. It happen on acids and happen also in natural product. This is quercetin or camphor or erythrin. All these are flavonoids. When you have flavonoid and you have on the position number 5 a hydroxyl, this hydroxyl make an intramolecular hydrogen bond with this oxygen, which appears at maybe 11, 12, 13. So if you isolate a flavonoid and you send it to NMR and you see a sharp singlet on 11 or 13, it's very sharp, by the way. You know this is you have a hydroxyl group on position 5. For example, this is a patylatin. A patylatin is a major flavonoid in Tagetes spatula, and this is the proton of number 5. The effect of concentration of the solvent and temperature of course, it's affecting. If you send it to the proton and you need to have a clear splitting system, don't make it over concentrated. If you send 20 milligram is a very good amount. But if you send it to the carbon, it's okay to make it over concentrated, not like the proton. The temperature effect, of course, but not much more. But it's effect in cases like intramolecular hydrogen bond. When you increase the temperature, it decreases. If you have the ketoenotourism, when you increase the temperature, the ratio between each compound is differs, differs of course. The type of solvents is differs. So when you work on a natural product, you isolate a compound, and this compound maybe you are not you wanted to make sure if it's new or non compound, and you want to compare the data, compare this data between your compound you isolated and the published data on the same solvent, because the solvent has a tiny effect, but it's present. Okay, the last thing in this session we will talk about is type of protons, or and it's very important. We have three different types of protons. The first one is homotopic protons. What is homotopic protons? Like this methylene. If you look at this methylene, these two protons are the same, appears as one signal all the time, because even if you change this proton with another group like phenyl, it's not a chiral center here, because we have two methyl group. We know the chiral center is the carbon which attached to four different groups. So these carbon are not chiral, so these protons are homotopic. They are the same, appears as one signal. These protons are not the same one, because if we change this proton and put a phenyl, it will be a chiral. So we call enantiotopic proton. And the enantiotopic protons also appears as one signal. This methylene appears as one signal, but they may have different chemical shift for each proton if we put it in a chiral media. Like if we use Musher ester reaction, and you put Musher agent, it would be different. But mostly it appears as one signal. The difference is here. If you have this methylene group and you have on the same compound another chiral center, so we have a methylene group and we have a chiral center. These two protons are not the same. These two protons are called distereotopic protons. And distereotopic protons not appear on the same chemical shift. Each proton from this one and this one will has its own chemical shift, and they will affect each other, and they will split each other also. So you have to make sure about this one. If you look at this compound, this work we made it and we published in Journal of Tetrahedral. We isolated four new compounds from 1 to 4. If you look at the difference, this R2 In compound 1 and 2 and 3 is proton, but and 4 is proton, but in compound 3 it's an alpha hydroxyl. So for 8 it should be enantiotopic in all of the compounds 1, 2, and 4, which means in 1, 2, and 4 it appears as one signal. But in compound 3, it will appear as two different signals. Why? Because compound 3 has a chiral center here. When this R is alpha hydroxyl, that means we have a chiral center here. And let's look at the table of the result. Compound 1, 2, 3, 4, 8, it's one here, one signal here, but here is two signals, 8A and 8B. And it differs because it's a chiral center. This is a pivot, antileukemic alpha proton derivatives from the endophilic fungus, Alternative Plasmospora, and contains this. Another example for the diastereotype proton here. So you look at a compound. Oh, here there is a chiral center here. What does it mean? It means that protons of 4 will appear at two different positions. Each proton is appear at a position, and they will split each other. And also 8 will appear at two different positions, not only one. If you look at this proton, we have a chiral center here. So this messenger and this messenger will appear as both of them at two different positions. Also here we have a chiral center here. So proton A and proton B appears as two different positions and split each other. If you look at this is a very complicated data because proton A, proton B, and methyl group and C, each one split the other one. It's very hard. If you look here at this compound, we have a chiral center here, either R or S. But this methylene and this methylene will has a different. Another one, the type of the stereoisomerism. If you have this one, this proton will appear at, if it's S, it will appear at position, and if it R will appear at another position. This one is much clearer. In the case of this one R, this proton appears as doublet of doublet here, and in case of S, it will be doublet of doublet here. But the change in stereoisomerism from R to S make a considerable change, but it's small change, not a major change. So if you are working with natural product and you comparing your data with another one, the first one published the R chiral center of this compound, and you have the same data except a little bit difference, but it will be considerable in proton and carbon. In the chiral area, the chiral proton or the chiral carbon, I'm sorry, and its proton, you have a new compound. You can say I have a new compound just by comparing the carbon 13 and the proton NMR, but it has to be in the same solvent. Of course, if you have another method or another things to prove your the novelty and of this compound, it will be much better. Proton on alcohol and the carboxylic acids and the amines also are exchangeable. What does it mean exchangeable? When I make it with deuterium oxide, when I put it in the deuterium, it's changed with the deuterium, which means it doesn't appear. What can I take from this? If I has, for example, if I have a sharp signal, and I'm not sure is this signal for the amine or for the hydroxyl or for another carbon. I just repeat the my experiment, okay, in an exchangeable solvent, and it should be disappear. Of course, if I make HMQC or HSQC in 2D, I will know clearly and easily. But this is not the situation here. This is a table of chemical shift. I wanted to make sure when I look on proton NMR, this area around one is methyls sp3. The area from 2.5 to to 4 or something like that, it's methylates. About the two, the area from 4 to 6, from 4.5 to 6, it's olefinic area, double bonds. From 6 to 8, it's aromatic. After 9, after 10, it's acids, aldehydes, or chelated protons like the the 5 hydroxyls in flavonoids. So this is the first look, and we wanted to learn how to use it. This is different chemical shifts for major things. I will put for you this photos in the group today about chemical shifts. Last thing is intensity of signals. Last thing today, and is integration. And I wanted to say, is it okay to complete the session or take a rest? Answer me on chat if you wanna. Is it okay to complete the session right now? Okay, Fatima said sure. I don't know, and I don't. I'm not sure if you need take a break. Take a break is would be better. Abdullah, yes, I think it's much better if we take a break. Who also is wanted to take a break? Okay, I think it would be much better if we take a break. Okay, thank you for joining me on this webinar, and I hope we got some benefits. We will take a break, and we will take a break right now, and after maybe 15 minutes, we will continue the second part or the third part of our lecture or our webinar. Thank you very much for joining me, and let's be here after 15 minutes. Goodbye.